Hello. In this video I intend to cover the AQA GCSE Science A Physics 1, and I'm going to cover in this particular video P1.1. So in this we're trying to cover the fact that the transfer of energy by heating processes and the factors that affect the rate at which that energy is transferred, and that could be broken down into infrared radiation, kinetic theory, energy transfer by heating, and heating and insulating buildings. So we're going to take each of these in turn, and I'm hoping to put together a series of videos which will cover all of the requirements for the Science A specification eventually. Straight into this, when you feel the heat from a fire, what you're actually feeling coming off there is the infrared radiation. Okay, so coming off that fire there, we've got infrared radiation, sometimes summarized IR or abbreviated to IR. So there's the infrared radiation being given off. The temperature, colour and shininess of an object all determine how much radiation is given off and how much it actually emits. Okay, so we have a requirement to know that all materials emit and absorb infrared radiation, that the hotter an object is, the higher its rate of emission. Okay, so temperature is going to be a clear factor. To know that matte and dark coloured surfaces are good at absorbing and emitting infrared radiation. And that shiny and light coloured surfaces are poor at absorbing and emitting infrared radiation. Okay, and also, and we'll look at this when we look at insulating buildings in particular, to know that shiny and light coloured surfaces are good at reflecting infrared radiation, and that becomes very important there. So using an example here of a recently parked car that's been driven around for a while, when it's immediately parked, it's going to be hotter, and we're going to get more of an emission of infrared radiation from the bonnet of this car. Okay, if you were to consider this car perhaps an hour or two later when it's cooled down, then the amount of radiation is going to be far less. Okay, the amount of infrared radiation given off is going to be less. What I'm trying to make is that the hotter an object is, the more radiation that it actually gives off or radiates in a given amount of time. It's also important to point out that the car bonnet will also be absorbing infrared radiation from its surroundings, but because it's temporarily hotter than its surroundings, then overall it's going to be emitting more infrared radiation than it's absorbing, and I think that's a key point to make. In addition to the temperature of an object, its colour and texture will also influence the amount of infrared radiation that's been emitted. So dark matte surfaces are much better absorbers when compared to light shiny objects. They also emit much more infrared radiation at any given temperature. Okay, so they're much better at actually giving some of this energy off when you compare them to a light shiny object. Shiny surfaces, they reflect a great deal of the infrared radiation that actually falls on them, and this makes them very, very useful in terms of reducing the amount of energy transferred. Okay, so if you're looking to reduce that, that's the colour and texture that they should be. I'll talk in more detail about the vacuum flask. It's a very common past paper question, and I mean in 2013 in particular it springs to mind. But you can see this makes use of the fact that silver surfaces are very good at reducing the amount of energy transferred by radiation, because they have this silvered surface inside the vacuum flask. And you'd have a question to explain each of the design features on the flask, and that would be one of them. Okay, we'll talk about the vacuum, we'll talk about the plastic cap when I talk about conduction, convection and radiation in a little while. So now we're looking at kinetic theory. So this is something you'd have covered many times throughout school in various years, but to know the three states of matter, the solid, the liquid and the gas, to know that the particles in each state of matter have different amounts of energy, to be able to use kinetic theory, so it gets a little bit trickier, to explain the properties of a solid, a liquid and a gas. And then finally, to understand and recognize simple models, which I'm going to draw in a minute, showing the differences between the particles in each of the three states. Starting with the solid, there are some points you want to raise. You can see the sort of uniform structure I've got there, and some of the features. We've got very strong forces of attraction holding the particles very close together. So we've got these very strong forces holding them together. The particles are very close together. In fact, I probably should have squeezed these circles representing the particles even closer together than they are there. A very fixed, regular arrangement, and obviously they've still got energy. It's not absolute zero where the particles lose all their energy, but they're going to be vibrating on the spot. Okay, I wish I could animate that for you, but obviously not possible in this format. Hopefully with the liquid you can see some differences. We haven't got the fixed regular arrangement, but the particles are still very close together. Much weaker forces here as a result of the energy within the particles. Okay, so some of the properties there we've got, as I said, weaker forces, particles are close together, they can slide and move past each other, but they usually form this irregular arrangements, and the clear point that they have more energy than those particles found in the solid state. Okay. Now in the gases, you can see the particles there, very spread out now. Almost no forces of attraction between the particles. They've got much more energy, and it is normal to try and show this or demonstrate this, by putting some sort of whizzy lines on them to try and show that they are moving about with lots of energy. So these would be darted around all over the place. They're free to move, they travel in random directions and at very high speeds, and they have a much higher energy, amount of energy compared to liquids and solids. Okay. Now when you heat a substance, what you're actually doing is giving the particles more kinetic energy, which is going to make them vibrate and move around more quickly. Okay. Now this is going to result in these particles breaking the forces of attraction, losing that structure, that arrangement that we talked about already. And you can see there, as we put more and more heat into this substance, you can see there that we're going from a liquid and eventually into a gas. Okay. Talking about some of the properties of the states of matter, a liquid and gas are able to flow, whereas a solid cannot. Okay, they can flow because their particles can move past each other. The particles in a solid can't move anywhere, they can only vibrate in a fixed position, as we already said, so they're not able to flow. And the other property I want to mention is the fact that gases are compressible. Okay, they're very spread out, which means you can squash a gas into a smaller volume. What you would do, you would obviously reduce the distances between the particles when you do that. Okay, because the particles in a liquid and in a solid are already as close as they can pretty much get, they can't be easily compressed or compressed at all, in fact. So far about energy transfer by heating through infrared radiation and the impact of temperature, colour and texture as a factor in determining its rate. What we'll now look at is energy transfer by heating through conduction. and then we're going to be looking at convection. Okay, and on the whole, energy is mostly transferred through solids by conduction and to liquids and gases through convection. Both types of heat transfer happen because the particles in a substance are able to move and move about. Okay. So when you heat a solid, you give its particles extra kinetic energy and cause them to vibrate more. The particles collide with their neighbouring particles and pass some of their extra energy onto them. Okay, this is called conduction. So you can see there we've got heat over this side, and eventually that heat is going to be passed on to the far end of this solid, whatever this solid is. Okay, so these particles vibrate more, and then they're going to bump into their neighbours, and their neighbours are going to take some of that energy, and then they vibrate in and bump into their neighbours, and this gets passed on and on. Now, how fast this happens, its rate of conduction is usually faster in denser solids. Okay, so the denser they are, the closer the particles are together, and so they're going to collide more often and pass on their energy. Materials that have relatively large spaces in between their particles will conduct heat much more slowly. They will conduct it, but it'll be more slowly, and they are considered to be insulators. Metals are very good conductors. They conduct so well because they contain free electrons. Okay, and these electrons are able to move inside the metal. So at the hot end of the object, whatever it is, the electrons move faster and collide with other free electrons, transferring their energy. Okay, so these other electrons then pass on their extra energy to other electrons and particles in the solid, and so it goes on. As a result of these free electrons, this is a much faster way of conducting heat energy through an object. Okay, so this is why heat energy travels so quickly through metals. A classic experiment, by the way, would be to be heating this up using a Bunsen burner, and you'd normally have a drawing pin or something similar attached with wax from a candle at this end, and you would time how long it takes for the drawing pin to actually fall off. And this is a great way if you wanted to compare different metals to see which are the fastest conductors, and that's quite a common experiment which could come up in the exam. So in convection, more energetic particles in a liquid or gas move from a hotter region to a cooler region, taking their heat energy with them. And this is possible because in gases and liquids, the particles are free to move around. They can slip and slide past each other, and therefore transfer their heat by convection very easily. Convection cannot happen in solids because those particles can't move about as much. They can only vibrate in their fixed position. Okay, so immersion heaters in kettles or hot water tanks work by using convection currents, and we're going to talk about these. Now, I'm sure you've seen this experiment or one just like it in school, and we'll just talk through this now. So what's going to happen, that heat energy from this Bunsen, from this probably smaller than usual flame to do this, if you want to see this process as we do, heat energy is transferred, and the particles near to this point are going to get more energy. So they're going to move around more quickly, they're going to vibrate more quickly, and they're going to start sort of sliding past each other more quickly. This means that the distance between them is going to increase. The water at this point is going to start to expand and therefore become less dense and rise. Okay, so less dense. So they're going to rise up. Okay. Convection in density means it's going to rise above the cooler water. As that hot water rises, cold water is going to sink towards the bottom. Okay, so we're going to get this sort of process going on, this current, and by putting potassium manganate crystals in there, which are purple when they're dissolved, you can see this very, very clearly. Okay, if you leave it too long, it all goes purple and you can't see it. But if you just get a nice convection current going, you should be able to see that in your beaker, and I'm sure you've done that experiment at some point. So we get the same thing here if we were switching a radiator on inside the house. These particles are getting extra heat energy, kinetic energy, they're moving around more quickly, therefore they're going to expand, they're becoming less dense, so they're going to rise above their colder particles down this point. As they move along, they're going to lose their energy, especially by a window or something like that, and they're going to sink at this point, so we get these currents going on inside the room. And they do like to use heating a house as an example. Asked about explaining this, just remember that it is all to do with the density of the particles, to the fact that they've got more energy, they expand, they become less dense, so they rise. Moving on now to condensation and evaporation, there is a requirement that you be able to explain each of these processes using our models of solids, liquids and gases and kinetic theory. So I'm sure you've noticed on a cold day when you breathe out you get that mist coming out with your breath. Okay, that's condensation. When you have a cool drink on a warmer day, then you get condensation forming on the glass. We need to be able to explain exactly what's going on in terms of the particles within condensation. So it's a situation where you have a gas cooling down, and the warm moisture hitting this cold glass is a good example of that. The particles that actually hit the glass will slow down, will lose their energy, their kinetic energy. This will result in the attractive forces able to pull those particles closer and closer together, and if the temperature is cold enough and the gas particles get close enough together, then condensation takes place. So it's the transition of a gas to a liquid that we're trying to describe. So the steam that you see from a kettle, for example, the water vapour, when it is a gas, is actually invisible. What you see when you see steam is actually that gas condensing back into a liquid as it hits the cooler air above the kettle. So there might be another example that you could be asked about. Remember, it's all about the particles. We need to be talking about what's happening with those particles in order for these changes of state to take place. Now, evaporation is when particles escape from a liquid and form a gas. And I just want to make the point that the particles can evaporate from a liquid at temperature lower than boiling point. It's a common misconception that people think, for example, with water, it's got to be 100 degrees before this process happens. I mean, we do get evaporation at much lower temperatures than that. I just want to make that clear distinction. Apologies in advance for my dodgy diagram there. I'll have to work on my artistic skills, I think. So evaporation will occur only if these two things are correct. So it's first of all the particle in question. If you're looking at one of these particles, they have to happen to be travelling in the right direction. Remembering they can be going and whizzing around all over the place. So taking this particle there, for example, even if it's travelling fast enough, has enough energy, the fact that it happens to be whizzing this way, it's never going to evaporate. It's never going to break out of those attractive forces from the rest of the liquid. This particle here might be going in the right direction, but if it's not travelling with enough energy quickly enough, if it's just bashed into another particle, then it's not going to make that leap to actually break away from these attractive forces, whereas this particle clearly is both going in the right direction and has enough energy to break away from those attractive forces. Another point I want to make is clearly this particle, if it does move away from the liquid, is taking energy with it, okay, and because it's taking that heat energy away from this body of water, then that's going to cause that water to cool down. Okay, and this is exactly what happens when we sweat during exercise. So that's another common question they like to ask about, when, why do we sweat? What are the benefits of sweating? And you need to be mentioned that the particles containing heat energy move away from the body and actually cool us down and help maintain that body temperature. I mean, that's maybe a biology question more than a physics, which shows what my background is, but I just wanted to mention that here. Now, the rate of evaporation is going to be higher with these three factors. Okay, so if the temperature of the water is higher, the higher that goes, the more easily evaporation can take place, because these particles are going to be whizzing around with a lot more energy and break out of those attractive forces more easily. If the density of the liquid being heated is lower, so the lower the density is, normally the forces of attraction between the particles will also be less, will be weaker. So more particles will be able to break out through the surface. And then finally, looking at surface area, if I have a beaker this size with a set volume of water, and I have a container this size with the same volume, hopefully you can see that evaporation is going to be much more easy and much more likely to happen in the container with the larger surface area. The final subtopic I want to cover for P1.1 today is heating and insulating buildings. And before I go into the details here, I just want to get across a measure that we need to know about and need to use and to understand. Fortunately, we don't have to calculate this, but U value is a measure of how effective a material is at insulating. So the better the insulator, the lower the U value, and this becomes very important when we look at insulating houses. There is from the building standards, there's a set U value that the house must have, and if the U value for that house is too high, then something needs to be done. We need to add insulation, we need to add some sort of way of lowering the U value to ensure that that house is a bit more energy efficient at keeping warm. And in a poorly insulated house, this diagram just shows how lots of the heat is lost. So 25% through the roof, 25% through doors and windows, 35% through outside walls, and 15% through the floors. And we need a bit of an awareness of what can be done to lessen these losses as much as possible. So there I've listed some of the ways that we can try and prevent heat being lost from this house, so including cavity wall insulation, where the gap between the inner and the outer wall is filled with some sort of insulating material. Loft insulation there, so if you haven't got loft insulation, you should get some of that put in there. Draught proofing around doors and windows, any gaps could be covered or filled in. Double glazed window as opposed to single. And if there was a hot water tank somewhere in this house, my feeble attempt to draw one there, to prevent heat being lost from that tank, if you cover that with some sort of insulating material, that will hopefully keep that tank warmer, meaning it takes less energy to heat it up. And what you're likely to be asked for each of these, and they could choose any, is what would be, how long would it take to be worth having this done? So for example, if it cost, well, let's say it costs £490 to have this done, okay, and that saved you £70 a year, okay, how long would it take for that to have been worth done, and how long would you have to live in that house for it to be worth having that cavity wall insulation done? And the sum that you need to do, which we can call payback time, would be 490. This is why you should always have a calculator in the exam, by the way, unless you can do this in your head. I can't. And that would take 7 years. Okay, so if you're staying in a house for 7 years or more, or plan to, and it costs £490 to to have that done, then you should get that done, because after 7 years it's going to start saving you money on your heating bills. Most cost-effective methods are those which are the cheapest to install, because they would have a very short payback time. So something like double glazing for, I guess, an average sized house might cost something like £3,000, which might save you £60 a year, let's say. Can you see that's going to take 50 years to pay us back? So if you're living in a house and you're not planning on staying in for 50 years, you might actually think it's not worth having that double glazing done. But these are the sorts of calculations that you could be asked to do, so it's worth practicing them. Another way of saving money on your energy bills is to use free energy sources to heat your home, and solar panels is an example that's mentioned in the specification. So what actually happens here is that we've got cold water is pumped into the solar panel, and it will be a matte black colour texture, and as we've already discussed, that makes it very, very good at absorbing infrared radiation from the sun. That infrared radiation will heat up this water, okay, and by underneath the solar panel, that point there will probably be shiny or light, because that will reflect any heat back out to help heat the water again as well. So we've got matte black on the top to absorb, and underneath it would be shiny. So just referring back to those differences between those two. That's going to heat up the hot water, and that hot water might be used to actually heat the house up, or for domestic hot water. Our solar panels work by absorbing infrared radiation, and that increase in temperature is used by the houses for heating or for your domestic hot water. And the amount of energy required to raise the temperature of 1 kilogram of water by 1 degree, that is known as the specific heat capacity. I'll say that again, specific heat capacity. And we need to be able to calculate this using an equation. The good news is that equation is given in the sheet that you will have along with the GCSE paper on the day. So there's no requirement to memorize this formula, but you must be able to manipulate it and insert the numbers to actually make your calculations. The equation, and I've spaced it out because I'm going to write underneath what each of these represent. So the capital E there, that's the actual energy transferred. Small m is the mass of the material that you're dealing with. C is the actual specific heat capacity, and this symbol, Greek letter theta there, is the temperature change. So I'll just write those in. Here's the definitions of those various units. If you're doing higher tier, then you will have to rearrange this formula. Okay, so you might have to calculate the temperature change and rearrange this so you can work that out. Okay, I'll give you one simple example for the foundation though. The specific heat capacity of water is 4,200 joules per kilogram degrees C. And the question is, how much energy is transferred or is needed to heat 2 kilograms of water from 10 degrees up to 100. So I want to take it up to boiling point. How much energy will I need to do that? Plugging those in there, you can see the mass in kilograms is 2. Multiply the specific heat capacity, which they'll give you. And the only tricky bit which will catch you out is the tendency for people to put 100 degrees there, remembering that we're actually looking for the temperature change. So it's 100 take away the initial starting temperature of 10, so it's going to be times 90, and that's going to equal 756,000 joules. So that's the end of 1.1 for Physics Unit 1. I'm going to continue trying to upload some of these videos. It's as much as for myself as it is for my students, in that I'm a biologist by training, and I'm teaching physics for the first time in quite a while. So I'm finding by going through this myself, it's going to help my teaching, and I'm hoping the students will find it of use as well. Thank you.